This is the second half of 9.1 through 9.3. We're going to do two things: solutions of homogeneous linear systems of equations and a little bit of determinants. Okay, solve a linear system given by this matrix equation. Give one non-zero solution without fractions. So if we dot and take this product here and set it equal to 0, 0, we get two equations. Negative 2k1 plus k2 is 0, and negative 6k1 plus 3k2 is 0. Now notice this equation here is 3 times the first equation. When you take a scalar multiple, non-zero scalar multiple of an equation, you're not adding any information. So this equation is actually unnecessary. It's not adding any information to the linear system. It's just a multiple of the first equation. So when that happens, you can just ignore the second equation and take a look at what the first equation is showing you. So if you solve this equation for k1, you get k1 is 1/2 k2. So in general, solutions look like any k2, and then k1 is 1/2 k2. If you're in linear algebra, we would call k2 t, give it a name, it's a parameter. But in this class, we're just going to keep calling it k2. So our solutions look like 1/2 k2, k2 for any k2. Okay, so let's pick the smallest k2 that will clear out fractions, because we just want one non-zero solution without fractions. We don't want infinitely many. This is infinitely many solutions here I've described, because you could take k2 to be, 4, in which case you get 4, 2. You could take k2 to be 2, in which case you get 1, 2. You could take k2 to be negative 1, in which case you get negative 1/2, negative 1. So just the simplest choice, I think, is taking k2 to be 2, and we get this vector here. Okay, so pause the video and give this one a try. All right, so hopefully you actually did that. And for part A, we're going to write out the linear system. It gives us 3k1 plus 2k2 is 0. Negative 9k1 minus 6k2 is 0. Again, the second equation is a multiple of the first. If you take the first equation and multiply by negative 3, you get the second equation, so we can ignore that. Well, actually, the answer to part A, negative 9k1 minus 6k2 is 0. So that's the answer to A. For B, if we're solving, we can just ignore this equation and look at the top equation. Solve for k1. k1 is negative 2/3 k2. All right, solve the system, give the answer as a vector with k2 as the parameter. So our answer is k1, k2, well, I'll call that big K. Big K equals negative 2/3 k2, k2. So that's the answer to B. And then C, give one non-zero solution without fractions. So I'm going to let little k2 be 3, and then big K is negative 2, 3. That's the type of computation we'll have to do in section 9.5. We'll have infinitely many solutions, and we'll just need one vector without fractional entries, and so that's what we'll do. Okay, crash course on determinants. We've all done determinants because you took math third semester calc, and we had to do 2x2 determinants in that class. The notation is straight bars. So straight bars means determinant. Okay. There's no E on the end there. It means determinant. So there are two notations, straight bars around the matrix, or leave the brackets and write DET in front. In each case, it's just AD minus BC. It's a number. Okay, so let's look at an example. Find the specified quantity, the determinant of this matrix. Okay, so we take AD, which is -2, and we subtract BC, which is -6. 6 minus 2 is 4. Okay. Seldom will we have one that simple. Typically, we'll be finding the determinant of A minus Ri. So, a problem like this. So, here's A. So, A minus Ri. We did this in the first part of the lecture. When you subtract R times the identity from a matrix, you end up subtracting R on the main diagonal. So 1 minus R, 3, -2, 2 minus R. So we want the determinant of that matrix. I'll use straight bars here. This is 1 minus R, 3, -2, 2 minus R. All right, that's 1 minus R times 2 minus R plus 6. And I said plus because it's minus a -6. So that's R squared. And then the middle term is going to be negative R minus 2. So minus 3R. And then I'll have plus 2 plus 6 is plus 8. There's our determinant. Okay, let's take it a step further. In section 9.5, we're not only going to find the determinant of A minus Ri, but we'll be setting it equal to 0 and solving. Okay, so we're going to take step B one step further. So here I have a different matrix. So find the values for which determinant of A minus Ri equals 0. So we're going to start out 0 equals the determinant of A minus Ri. So in the determinant symbols, I'm going to write A minus Ri. So subtract R on the main diagonal. So that's the equation. This is 0 equals determinant of A minus Ri. I want to solve that for R. All right, before I can do that, I need to multiply it out. So that's 1 minus R quantity squared minus 4. So that's R squared minus 2R. Then plus 1 minus 4 is minus 3. All right, we're going to have to factor that. R minus 3, R plus 1. For those of you in Math 3A, this is called the characteristic equation. So we're solving the characteristic equation for R, and this gives us R equals 3 and -1. Also, if you're in math, in linear algebra, these are the eigenvalues. And even if you're not in linear algebra, we're talking about eigenvalues in section 9.5. So what we did is we just found the eigenvalues of that matrix. All right, and that's it for these lecture notes.